Religion, morality, and knowledge, being necessary to good government and the happiness of mankind, schools and the means of education shall forever be encouraged. University of Michigan Television presents Understanding Numbers, a history of man's use and enjoyment of numbers from ancient bartering to amazing new calculators in this atomic age. Your instructor is Dr. Philip S. Jones, Associate Professor of Mathematics. Program 3, Big Numbers, a discussion of how scientists write and use big numbers, together with a mention of the imaginary Google and Googleplex. Now here is Professor Jones.
Today we'll talk about a topic which has fascinated men through the ages: the very large, very small, and the numbers that can be used to represent them. Perhaps the earliest experience in history that has been recorded of a man working with very large numbers goes back to the Greek scientist, physicist, and mathematician Archimedes, who as early as 230 years before Christ found himself fascinated by the problem of could he, with the clumsy Greek numeration that was in use at that time, write a number as large as, and he thought of a big number, the number of grains of sand that it would take to fill the universe. He imagined how long it would be from the earth to the sun. He also assumed a very small size for a grain of sand. And then by working out a system of grouping smaller numbers into larger ones and then again into still larger ones, into groups that he called periods, in which he solved this problem of how to represent a number as big as it would take to tell of all the grains of sand that would fill the entire universe. 1,000 years later, we find the Hindus, the people from whom our number system was derived, fascinated still and again by large numbers, to the extent that they invented many number names. In fact, they invented a separate number name for every different place of our decimal place value system of notation, so that where we sometimes say thousands, tens thousands, hundreds thousands, using the word thousands over and over again, the Hindus had a separate name for every different position. Perhaps one of the nicest stories that illustrates this point is that of the education of the young Buddha. Sir Edwin Arnold, in his book called, in his long poem, in fact, called The Light of Asia, relates the education as it is in Hindu mythology of the young Buddha. Taken from his poem, we have here a scene in which Buddha's teacher, Vishwamitra, is listening to him recite his lesson. It runs as follows: "And Vishwamitra said, 'It is enough. Let us to numbers. After me repeat your numeration till we reach the lot. 1, 2, 3, 4, to 10, and then by tens to hundreds, thousands.' After him the child named digits, decades, centuries, nor paused the round lock reached, but softly murmured on. Then comes the Koti, Nahut, Ninahut, Kamba, Vishkamba, Abad, Atata, to Kumuds, Gundhikas, and Utpalas, by Pundarikas unto Pundumas, which last is how you count the utmost grains of Hastagiri ground to the finest dust. But beyond that, a numeration is the Kata, used to count the stars of night, the Kodikata for ocean drops, Inga, the calculus of circulars, Sarvana Chepa, by the which you deal with all the sands of Gunga till we come to the Antakalpas, where the unit is the sands of 10 crore Gungas. If one seeks more comprehensive scale, the arithmetic mounts by the Asankhya, which is the tale of all the drops that in 10,000 years would fall on all the worlds by daily rain. And thence unto the Matakalpas, by the which the gods compute their future and their past. And master, if it please, I shall recite how many sun motes lie from end to end within a yojana. Thereat with instant skill the little prince pronounced the total of the atoms true. But Vishwamitra heard it on his face, prostrate before the boy. For thou, he cried, art teacher of thy teachers. Thou, not I, art guru. Now this fascination for large numbers amongst even children is further depicted by an event that some of you read in the newspapers some years ago, in which Edward Kasner, a mathematician at Columbia University, was having a fine time talking to a bunch of kindergarten children. It happened to be raining, and he suggested that the number of drops of rain that were falling on New York at that time would be an interesting thing to talk about. The children decided that this would be a tremendously large number, but still not infinite. And they discussed the difference between infinity and a finite number. Someone said, well, we ought to be able to write these. And a large number suggested by one of the children was thought to be 1 followed by 100 zeros. But no one knew a name for it until one of the children suggested, well, let's call it something. We make up a name. They called it a Google. But then the children said, there must be still larger numbers. In fact, someone said 1 followed by a Google of zeros is something we can talk about and write about. And next, another child suggested we should have a name for it. And thus was born the word Googleplex, for 1 followed by a Google of zeros. Now actually, large numbers are not only interesting and fascinating, but they are tremendously useful in many areas of mathematics. Of course, scientists do not use these words Google and Googleplex, but they do have schemes for writing large numbers. The importance of these large numbers are displayed by some of them which we have written here. The first one may leave you with a few shudders, it being our national debt. The second ones are the places where large numbers are used more commonly by scientists, are at least 2 examples. The first of these, which I will not attempt to read for you now because I'm going to show you an easier way of doing it, is the number of miles that a ray of light will travel in a year, of interest particularly to astronomers. The second is the number of atoms in a small amount of hydrogen, the sort of thing that physicists and chemists are concerned with. But to find an easy way of writing and computing with these numbers, we need to have a few new ideas. If you will turn over here with me, I'll introduce you to them quickly. If 2 numbers are multiplied together, such as 3 times 4, we call each of those numbers a factor. 3 times 4 is 12. 3 and 4 are both called factors of 12. Sometimes it's convenient or necessary to have a factor repeated. 3 times 3 represents 3 used as a factor twice. Mathematicians then find it convenient to write this number with a notation in which they represent the 2 factors by writing a small 2 above and to the right of the 3. This small 2 is called an exponent, and the whole expression, 3 with the exponent 2, is read 3 to the 2nd power. If, for instance, I were to want to multiply 3 tens together, I could write that much more quickly and compactly by writing 10 with the exponent 3 and saying this is 10 to the 3rd power. Or if I choose to use letters to represent numbers, I could write A times A times A times A. A used as a factor 4 times would be much more quickly and compactly written as A with the exponent 4, or A raised to the 4th power. Now, to see how these ideas are going to be used to write large numbers, we have to go back and review 1 or 2 ideas from elementary arithmetic. If 4 were to be multiplied by 10, you all recall that this is quickly done by merely adding a 0 after the 4. 4 multiplied by 10 to the 2nd power is the same, of course, as 4 multiplied by 10 and then multiplied by 10 again, and that we could easily write as 4 followed by 2 zeros. 4 multiplied by 10 to the 3rd power, we can skip now writing out these details and know that by a general procedure it would be 4 followed by 3 zeros, or 4,000. In all of these examples which we have had here, we have been able to multiply by 10 by merely adding zeros. This, however, was because we did not have any problems in which there was a decimal point. If we had had a different number, such as 2 and 836 thousandths, to be multiplied by 10, just adding a 0 would not have helped us. We would have had to move the decimal point 1 point to the right, giving us 28 and 36 hundredths. If we had had 2 and 836 thousandths to be multiplied by 10 twice, this we could have done by moving the decimal point 2 places to the right, writing 283 and 6/10. Thus we find we have a general rule for multiplying by 10 numbers that involve a decimal point and decimal fractions. Namely, for every time you multiply by 10, you move the decimal point one place to the right. A similar rule for division would be worth having available. If we had such a number as 23 and 56 hundredths to be divided by 10, the easy way to do that is to move the decimal point, of course, in the opposite direction from that for multiplication, namely to the left. And this becomes 2 and 356 thousandths. The same number, 2.56, divided by 10 to the second power would mean divided by 10 twice. In order to do that, of course, we would have to move the decimal point 2 places to the left from this position over to here, giving us 2,356 ten-thousandths. Now, with these ideas and words at our disposal, we are ready for the payoff. We're ready to see how a scientist can write big numbers quickly and concisely. Let us take, for example, the number of miles from the Earth to the Sun, which is approximately 90 million miles. Now, these zeros are not really very important, except as to show us the size of the number. It would be nice merely to write the 9 and to write it with a decimal point right after the 9. But obviously these two numbers are not equal, because in order to write just 9 with a decimal point immediately following it, I had to move this decimal point over to the left 7 places. This corresponds to dividing the original number by 10 7 different times. To offset that and to make sure that I have here exactly the same number that I began with, I must then multiply by 10 7 times. So that I now can say that 9 times 10 to the 7th is identically the same number as this 90 million, which I have written here. This, by the way, is sometimes called standard notation or scientific notation. And if we turn back to our original examples, we can see how they would have been written using this sort of notation. For example, our figure here for the light year, if we were to write it in scientific notation, would involve moving the decimal point 12 places to the left, giving us then 5 and 87 hundredths. But to compensate for moving the decimal point 12 places to the left, we multiplied by 10 to the 12th. And this number, which I wouldn't try to read in its original state, when written in standard notation or scientific notation, becomes 6.06 times 10 to the 23rd. This notation, by the way, will even make it possible for us to write quickly and concisely the thing which we call the googol. The googol, you remember, was 1 followed by 100 zeros. This then would be the same as 10 with the exponent 100. And so here we have, quickly and concisely, a googol. I wonder if we could write a googolplex. A googolplex was 1 followed by a googol of zeros. This then would be 10 with the exponent a googol. But we have just said a googol is 10 with the exponent 100. So 10 to the 10 to the 100th power is a nice, neat, concise way of writing a googolplex. Now, not only are large numbers important in science, but also very small numbers find tremendous uses. In order to talk about very small numbers, however, we'll have to add one additional idea. Namely, we'll have to talk about such a thing as point with, say, 4 zeros and a 5. How could we write this in the same manner that we wrote our large numbers, namely with a decimal point right after the first significant figure? If we were to start to do that, we would move the decimal point 1, 2, 3, 4, 5 places to the right in order to get it to follow exactly after 5. But this is equivalent to multiplying by 10 to the 5th power, by multiplying by 10 5 times. So to compensate for this, we would have to reverse the process and write after this 5 divided by 10 to the 5th power. But previously we used a multiplication sign, and for consistency and for mathematical beauty, we would like to continue to use the multiplication sign. This can be done if you will remember with me that dividing by any number is exactly the same as multiplying by the fraction you get by writing 1 over the number. So 5 divided by 10 to the 5th power can be written as 5 times 1 over 10 to the 5th power. And now at this stage, mathematicians and scientists invent one new symbol and one related idea to make it even simpler to write these large and now these small numbers. This new idea consists of saying we will call 1 over 10 with the exponent 2. We will write that as 10 with the exponent negative 2. And if I want to write 1 over 10 with the exponent 3, that I will define to be the same as 10 with the exponent negative 3. And now turning to our problem over here, you see that 5 times 1 over 10 to the 5th can be written as 5 times 10 with the exponent negative 5, after having given by definition a meaning to this negative exponent. Now, some of the instances in which these small numbers are used are indicated by the numbers which you see here on our chart. For example, the diameter of a red blood cell is given by this number of 8, I believe it is, hundreds, thousands, 10,000, 800,000. To write this in the form in which we have been doing this for our large numbers, we would move the decimal point from this position over to following immediately after the 8. In so doing, this now becomes 8 decimal point times 10 to the negative 5th. In order to compensate, the 10 to the negative 5th is to compensate for our having multiplied by 10 5 times. Now this number, again, I won't even try to read for you in this form, but see how neatly it is written using scientific or standard notation. It becomes merely 3 times 10 to the negative 23rd power. Now these numbers which we have written, these large and small numbers which we've written using exponents and the idea of a power, are also typical of many other uses of the notion of exponent and power. I have here, for example, several formulas which illustrate the other uses that this notion to which this notion may be put. For example, this first formula represents a relationship that was developed in studies of wounds during the First World War. S represents the amount of healing of a wound, is a measure at least of the amount of healing of a wound, and it was found that S equal to 5 2/10 times e to the negative 1500 t would help a doctor to predict whether a wound was healing properly or not. T representing the length of time that has passed, and this number E representing a mathematical constant somewhat like the pi that you studied in geometry. It actually is a number between 2 and 3. A second illustration is one that engineers will recognize. This is a formula for the friction between a belt around a pulley and the pulley itself. T1 and T2 represent the tension in the belt, which is being run by a motor perhaps. Theta represents the angle of contact between the belt and the pulley. And this formula then, again, uses the notion of exponent, which we have been talking about, the idea of power. Here is a different type of an illustration, the sort of thing that a biologist or bacteriologist would be interested in. It represents the number of bacteria in a culture T hours after this culture was allowed to begin its growth. It represents then the growth or the total quantity of bacteria in a culture that is growing. Another illustration comes from the realm of economics and sociology. It represents the population of one of our western cities. P is the number of people in that city. Here is our old friend that we mentioned a moment ago, E, this mathematical constant. T is the number of years after 1870. This formula was calculated to give the population of the city in the number of years after 1870. Here we have a formula that would be of use, is used by businessmen occasionally. This is a particular example of one way of calculating the value of a fleet of trucks after they have been in use T years. This sort of problem is important, for instance, in figuring income tax, where you have to allow for the depreciation or the wear and tear on your trucks as a part of your cost. This is only one way of figuring depreciation, but it is one that is useful, V being the value of the fleet of trucks, and T being the length of time after they have been purchased. This illustration calls to mind a story from history, which you may have met previously. It also is related to a formula that is of some interest to you. Some of you remember the story that the Dutch, when they first came to New York area, bought the island of Manhattan from the Indians. The story is that this was done in 1626 at a cost of $24. Now, some people have thought that the Indians were being gypped in this case, that the trinkets worth about $24 did not really pay them for the land which they sold. Especially they think this when they look at Manhattan as it is today. However, if you were to deposit $24 in a bank or buy a bond with it and then start to accumulate interest and compound the interest on it, you'd be surprised what would happen. The formula that applies here for the amount of money you would have at any time is that this amount of money would be the principal that you originally put in the bank times the quantity 1 plus the interest rate stated in hundredths, and this then raised to the nth power, where n is the number of years since you began to calculate the interest. Our particular problem about Manhattan says that if they had originally paid $24 for that island, and if we could somehow at that time have invested that at 4% interest, and if you calculate it and find that the number of years since then is 327 up till 1953, we have here the formula that represents the amount of money that would have accumulated from that $24 in this time. I'm not going to take the time to figure it out for you now, but if you'll take my word for it, it is almost, this symbol means almost, $9 million. Would you not have liked to have had a great-grandfather invest $24 for you in 1626? Of course, maybe $9 million is still not the value of Manhattan, but there have been a few improvements since that day that were not calculated in here. If we move still farther back into history, back to the time of the Pythagoreans before Christ, you'll find another interesting and amusing situation in which exponents play a role. The Pythagoreans built up a whole philosophy based on numbers, a rather mystical philosophy. Certain kinds of numbers they called perfect numbers. I'll define a perfect number by giving you an example. 6 is the first perfect number. According to the Greeks, the reason that 6 was a perfect number was that if you were to write down all of the other whole numbers which will divide 6, you would write down 1 and 2 and 3. And then if you write down all those possible factors and add them up, you get 6. In other words, 6 is a number which is equal to the sum of all of its possible divisors. And this is the definition of a perfect number. The second perfect number was also known to the Greeks. It was 28. The divisors of 28 are 1 and 2, not 3, but 4 and 7 and 14. If you add them up, you do get 28. You might think then that apparently there would be a lot of perfect numbers. But this is not true. Mathematicians, however, began to wonder how many are there and how can you find them? And only a little later than Pythagoras, still about 300 years before Christ, Euclid, whom you mostly know or think of as a geometer, gave a formula for perfect numbers. He didn't give it as I'm writing it, but he didn't use these symbols. But Euclid's formula says that you will find a perfect number if you take the number 2, raise it to the n minus 1th power, and multiply that by 2 to the nth minus 1. Let's try this for n equals 3. If n equals 3, this is 2 with the exponent 3 minus 1, or 2 with the exponent 2. That means 2 times 2, or 4. This quantity in here is 2 with the exponent 3. That means 2 times 2 times 2, which is 8. 8 minus 1 is 7. And so Euclid's formula for n equals 3 gives us 4 times 7, which is 28, that which we found to be our second perfect number. Now, if my tablet will rise up a little bit here, we will go ahead and calculate what this formula, p equals 2 to the n minus 1 times 2 to the n minus 1. Let's calculate what that would be for n equals 4. This would be 2 with the exponent 4 minus 1, or 3, and we know that 2 to the 3rd power is 8. This would be 2 to the 4th power, that, you can figure for me, is 16, minus 1 is 15. 8 times 15 is equal to 120. Now, I'm not going to take the time to go back and add up all the factors of 120. I'm going to disappoint you, in fact, I trust, by saying that 120 is not a perfect number. This doesn't mean that Euclid didn't know what he was about, however. It merely means that at the beginning I didn't tell you the entire story. Euclid said this formula will give you a perfect number as long as the number in the parentheses has no factors other than itself and 1, as long as this number is what is called a prime number. 7, for instance, was a prime. It had no factors. But 15 is the product of 3 and 5, and hence it is not a prime number, and Euclid himself said this formula does not work in that case. So this is not a perfect number. In recent times, the number of perfect numbers which have been discovered has been increased, in fact, in the last 3 years, from a total of 12, there being only 12 known perfect numbers for about the last 75 years, to a total now of about 14 or 15, I believe. No, 16 known perfect numbers today. The largest of these is the one that you will get if for n you substitute the number 2,291. Now, the one before this that was discovered is the one for which n is 1,279. The people who have worked with this said that it would take 100 years of work with a desk calculator to determine that the number represented by n being 1,279 was a perfect number. We were able to do this recently, of course, by the use of the high-speed electronic calculators, which we have mentioned to you before. There is, incidentally, one way of making yourself famous by playing with perfect numbers. The formula which Euclid gave involved powers of 2 raised to higher and higher powers. That meant that every perfect number in Euclid's formula had to be an even number, divisible by 2. 6 and 28, both are divisible by 2. Now, no one has ever found an odd perfect number, but no one has ever been able to prove that there is no such thing as an odd perfect number. If you can find an odd number such that it is equal to the sum of all of its divisors, you can make yourself famous. Now, today we've tried to explain to you the meanings of the exponent and power and some of the uses to which we put exponents and powers. We've also showed you something about the fun and fascination that go along with the large numbers. I hope you don't think that all of mathematics is computation or strictly amusement. The ideas of exponents and powers have many other applications in designing logarithms and slide rules. I'm going to leave you here for the moment, however, with just one puzzle, a famous one. What is the largest number you can write using only 3 digits? The first thing that most people say is 999. I'll just tell you this much, that's wrong, and leave with you until our next meeting the question, can you find a way to write a larger number using only 3 digits, a number larger than 999? I hope you have fun with it.
Thank you, Professor Jones. Be with us for program 4 of this Understanding Numbers series, when Professor Jones turns to basic arithmetic to demonstrate the interesting basis of our elementary operations in adding, subtracting, multiplying, and dividing. Sebastian speaking. This program was produced by University of Michigan Television for the Educational Television and Radio Center.